models in the switch and trying them. So now I think we wanted to end the sort of this day with a discussion with the panel, like with our esteemed panel from folks from architecture, networking, and ML to discuss what, like, why ML like is important and what's its role in networking as a whole. So we have Jen, Nick, and Kunle, all amazing folks, like doing awesome work in their areas. So I think I'll just start the discussion up front because it doesn't, like, we all know them, right? Like there's no introduction necessary here. So as the first thing that I think my question is for Jen, like, we have been like, so right now in the tutorial, the whole day, we have spent a lot of time enabling our community to sort of implement models in the network, like using Taurus and things that people have been doing, using P4, how to run ML model in the switches. But I think the question that everybody is asking, and the big question here is like, what role does ML play in networking in the first place? So do you have any thoughts on that?
Right. So I think ML can play an important role in network management. I mean, a lot of network management is anomaly detection or telemetry to understand the conditions of the network and adapt accordingly. And I think the intersection of that with programmability is quite exciting because I think it's really difficult to apply ML to the wrong data, right? If you have a very coarse grain, indirect view of what's going on in the network and very indirect and incomplete ways to exercise control over the network, you're spending a lot of your ML, if you will, on reverse engineering things you could have observed directly and coaxing the network into doing things you could have told it directly to do. And so I'm excited about this intersection because I think programmability really means that it's now possible to expose the features that are actually going to be important for detecting what's going on in the network, security problems, performance problems, reliability problems, and to also have the knobs in the other direction to affect control, to reroute traffic or drop traffic or rate limit traffic, that if you have the right dials and knobs, it now becomes possible to self-drive the network in a way that probably would have been unsafe and maybe impossible to do in a fixed function network where the knobs and dials are so constrained. I think there's still tons of challenges there to make sure that we can really trust the models to actually, tell us that not have false positives, to not have collateral damage on who we think might be responsible for an attack. So we're certainly by no means done, but at least by being able to co-design the ML with the network functionality itself, I think there's a hope to be able to do some really exciting things to make networks much more reliable and secure and efficient going forward.
Right. No, I think that's a very, very good point. So basically the thing is like ML is not just about doing it in the data plane. It has various other components like data, building the right models, making them like consuming the right amount of data and doing those things. So I think moving forward, like maybe I will start with Kunle, like being the architecture like a person. So where does the architecture come in here? Like, so the role is like we have architectures all over the place in the control plane, at the end host, and in the network. So how does like the ML for networking can play this role? Like how the architecture can participate in making this happen?
Well, I mean, I think architecture is always in service of some higher level application goal that one wants to achieve. And in this case, it's sort of providing the capability to do, line rate ML, right? And this is something you can't do today. And so if you could do that, then the question is, could ML unleash a whole set of capabilities that Jen just told us about? Could it make networks more secure? Could it make networks more resilient? Could it make them easier to manage? Could they do this all by themselves, right? So I mean, this is the goal, but until you've got the underlying architecture capability to provide the sorts of performance and in terms of the latency and the bandwidth of processing the models, and it's currently I think unclear sort of what complexity of models is really required, and also how much benefit one could get with more complex models, right? And so architectures that can provide much more efficient processing than max action tables, which are kind of what people do in networks these days, or so I'm told. I'm not. If you want to provide something that does linear algebra, then I think architecture re-architecting the network is the right thing. But I think, from an ML point of view, again, I'm an architect, right? I talk to ML people, I talk to networking people. These are all important applications, and the ML people say, hey, we want to make ML more accessible, more usable, easier to deploy, and they don't want people to focus on developing models. They want people to have declarative ML where they specify what it is they want to achieve, and the rest of the infrastructure should be something that the ML software provides. And I think underlying all of this infrastructure has to be architectures that can actually deliver the performance that you need.
Right. Okay, good. So I think clearly, so in terms of architecture, there is a lot to be done, and it seems like we need to bridge the gap between networking and architecture people, like have more people from architecture collaborating with us and doing those things. I'll move on to Nick. I think Nick, I have this question. So in the audience today, like a lot of questions were raised about, like, do we need ML? So ML helps where you don't know what is happening, right? Like you don't know a solution and you want some artificial intelligence to come in and build the solution for you. But in networking with heuristics and things, the question is like, I think the question they posed was like, we know what is happening. We know what the problem is. We know the traffic that is coming in. And so we can build very good heuristics. What is causing us to move into this ML space? So you working in network management, do you think like that statement is still valid today? Or like, how can we move about in this area of ML?
I'm reminded, I guess, and it relates a bit to your question to Jen, but I'm reminded of some work that one of my students, Makaram Bintarak, did like ages ago. You remember Makaram? And this was about predicting how configuration changes in a large CDN, starting with G, were affected by various could basically affect search response time. So if I deploy a new front end cache, right, or if I change the compression on the traffic, what's that going to do to how fast the search result comes back?
Right.
And that's an interesting question. And I think basically it was the first time I think that I had seen a problem, and that he had put to me that there is no closed form solution to this. You cannot this is not a TCP throughput equation, right? We can measure loss rate and latency and so forth. And I think Jeff Mogul and others had written many lovely papers and prior to that on modeling TCP throughput from things you could measure. But there was just no way to basically get a closed form solution to this. And so the only way to do it was basically to build models from the data available, right? Machine learning in a way is just pattern recognition, right? And I remember at the time thinking, this is really interesting. And other co-author, Makaram's co-advisor, Mustafa Amar, said, yeah, this is really cool, but can anybody who's not Google do this, right? What do you do if you don't have that amount of data? What do you do if you don't have that amount of compute? And I think to your question, is it still relevant, or is it still, well, it has been for 15, 20 years now. But I think we're actually faced with the same problems that we were back in 2007, 2008, which is like, yeah, it actually can work if you know what you're doing, if you have the domain knowledge to make sure your model's learning the right things.
Right.
And if you can basically have ways of dealing with that data. And that's, I think, where the architecture and the complexity comes in. Kunle mentioned something about complexity. And another story that I like to tell is that, everybody who comes in, wanting to do a project or wanting to take a class in machine learning and networking, they're like, deep learning. Tell me about deep learning. I'm like, well, let's try random forest first. Let's try k-nearest neighbors. We've got a paper in a deep learning and security workshop, and the dirty secret of that paper, if you read to the end, is that the deep learning models don't work any better than KNN. So, so I think this discussion that we were just having about model complexity is also really, really good thread to pull.
Right. I think this is a good point. And then clearly, but again, I think the perception here is that heuristics work Like, and primarily what I'm hearing from you is like, because the data, the lack of access to the data is what is causing us to still stick with these existing heuristics in some sense.
I'll say one, which is ML models are basically heuristics.
Yeah.
Linear regression, there's really like nice optimization math there.
Right.
A lot of machine learning models, if you look at clustering methods like DBScan or, even things like random forests, there's a lot of heuristics in there.
Yeah.
So there's no magic there. The magic is in really like the data wrangling, the data representation, et cetera.
Yeah. Yep. Sure.
So I agree with Nick's point about not having closed form solutions. So even if you have all the inputs, you just may be in a situation where the optimization problem or inverse problem you're trying to solve just isn't tractable, right? I mean, it's kind of what you're getting at. I totally agree. Another thing that can go wrong is that you're controlling just one portion of the system, right? You're one autonomous system or you're a CDN provider, but you don't control the other decisions that other actors in the system are gonna make based on your decision. And that's another place learning can come in, because you just don't have any hope of necessarily modeling that directly in anything approaching a closed form, because you don't have access to even the algorithms or protocols they might be running or how they might be affected by the things that you yourself do. And so I think that's another setting where you just have to let the data, at least in part, be your guide.
Yeah. So I like this idea of data driving things. I mean, I think, you look at deep learning in the areas where it, of course, has gotten the most notoriety in sort of image processing, image recognition, and natural language processing. For the longest time in those areas, people looked very skeptically at the DNN approaches, right? And I remember Jeff Hinton, when he got the Turing Award, standing up at the conference and giving a talk that said basically, you guys are wrong and I was right. But and but if you look at you look at sort of why he was right eventually was more data and more compute to build the models, right? And so you can see this happening in all of these spaces, and I think it's going to happen in networkings too, right? We're going to get more data, and we're going to get more computational capability. We're going to train these models, and we're going to do inference, and we're going to surpass the capabilities of the current set of heuristics, and I can see that happening.
Right. So, going back, so Milan, so I have a question for you. So,
all right, so I have one more point to chime in.
Can you hear me, Milan?
Hello, can you hear me?
Yes, we can hear you.
I have one more point to chime in. I think in addition to the complexity and data problem, one more problem that ML is especially good at is adaptivity. So even if we can come up with heuristics, we can only come up for a specific setting. But ML is adaptive for different types of networks, different types of data. We mentioned about small network versus Google, who have different amount of data. So I think if we develop one ML solution to help us to adapt to these different scenarios, while if you're coming with heuristics, then you would have to come up with one heuristic for one scenario. So it's a lot of work. And I think this adaptivity is also a good match for programmable hardware. So that allows us to better use the programmable architecture to support these diverse tasks.
All right. No, I think this is a good point. So basically, the thing is, like, what I'm getting from the discussion here is data, right? So how do we get that? Like, I think that's the main point. So ML, so this workshop has been primarily focusing on giving you compute capability so that you can do ML in the switch. But I think the challenging part here is, again, the data is what enables everything. So I'm seeing like sort of there are two things coming out of here. One is like, okay, not knowing. If you don't know what is happening, then you need ML, right? And if you know what is happening, then you can build these simple heuristics and balance yourself according to them. So not knowing means, like, is it true? Like, not knowing means having no data? Like, and if in that case ML is happening, like, how do we go about it? Like, so again, in general, my question is like, how do you think like we can make this data accessible? Like, how can we make, as researchers, get to that data and like start doing this research? Because again, in silos, we are doing some work, but to see an actual impact, we need to sort of have this real access to the data.
There are many facets, I think, to this question. So are you asking about, as researchers, how do we get access to offline data sets? Or are you asking about, as researchers, how do we think about getting data in real time in.
I think so. The question here is like in general for ML,
yeah.
how do we get the data so that we can show real impact and real sort of output?
That's a really tough question. I think. I mean, I think access to data is something that I think we've struggled with. I think as a community for a long time. I think one of the things that it's particularly challenging in this context is that it's not clear how well models transfer. Okay, so some of the work that I see it in network security all the time. We can pick on them, right?
Yeah.
You know, there's a model that's shown to, but it's true of network performance papers too that use models. Something works maybe particularly well on a data set for a paper, but it's not clear, you know, what that model has keyed into to perform so well. I'll give you an example. When we did this work called nPrint. Long story short, skipping ahead, we trained a whole bunch of models on various data sets, things to seem to perform pretty well for doing things like application identification, device identification, et cetera. When we looked at basically, you know, backed out the feature importances and stuff, it was like, oh, the models are keying in on fields in the packet header, like the time to live field and things like that. Well, what's that about? Oh, actually, it's not really learning anything important at all. It's basically just learning something that's very particular to the topology of the experimental setup under which the data was gathered.
Right.
Okay, so when you go back to your original question about how do we get the data, I mean, I think that's like an old question. Like we can all kind of like find data in the dark corners that we all go digging. The problem is like, if I write a paper using data that's gathered from the University of Chicago campus network, you know, someone looks at that model and basically has no idea, you know, Kunle could say, well, I don't know if that's going to work in my network. And I think that is a huge barrier for deployment in machine learning for network operations. Is even I read a paper with like a huge amount of skepticism when I see like, oh, like F1 score of like 0.99, that's clearly cooked, right? And I don't mean it's like faked. I just mean that's a closed world data set. The model has basically learned that data set very well. But like an operator, how are they to believe like that this is going to work on there? And I think that's a challenge that I think we really should be thinking about as a community. So that's not strictly an answer to your question, but I think one of the things is like, if I've got a model and a result that works for my data, and I write a paper, I publish a result, how's anyone else to, you know, how's anyone else to interpret that, you know, in general, right? We're supposed to be talking about generalizable results. This is science, right?
Yeah, just a follow up to that. First of all, I completely agree. I think it is true that we can sometimes get data from dark corners, but often one challenge there is we want fields that are not logged in that data. You know, we might want to go deeper into the packet contents or look at specialized fields in TCP or UDP that might not be in a particular data set. And here I think programmability can help. So just as an example, at Princeton, we have a bunch of programmable P4 switches deployed around the campus, connected to passive taps of the links in the campus. So not carrying the traffic live, but receiving a live feed of it where we can do the analytics directly in the switch. And what's nice about that is we can try out our ideas, but more importantly, we can access header fields that might not normally be in publicly available data sets, or even might be too sensitive even on our campus to log, where we can do the analysis directly in the switch and just compute the answers to the questions of interest without ever exporting the raw data. And so I think that has some important potential to help us in getting around the access to data and access to fields in the data. And going one step further, you could imagine addressing the reproducibility question. If a number of us at different campuses have an infrastructure like that deployed, then I could try Nick's algorithms on the switches in my network, and I could try mine and his. That wouldn't be possible if we were trying to share raw data sets, but it might not be crazy that we run each other's programs on the data sets that we have locally or collect live on our own campuses. Still hard, but at least better than, say, trying to get a public data set available on the internet that will have all the fields we want available to it.
Right. So Milind, do you have any take on this? What do you think?
Yes, so I think, on the one hand, this lack of data is bringing challenges for us, but also I think it's bringing challenges for machine learning people. If we can design new ML techniques that can tackle this small data problem or lack of data problem, that would be especially exciting. So for example, Nick mentioned like random forest sometimes works better than complex models. So that's, I think, partially because the amount of data networking problem typically have. So it'd be really nice if we can work with ML people to develop smaller, simpler models that are more robust to lack of data situations. On the other hand, we may also want to look for ML tools that help us generate adversarial scenarios, identifying which area we are lacking of data. So those kind of tools would help us to also test the robustness of our solutions. Yeah, so I think that it's actually a challenge ML and networking people can work together, not only networking people just keep exploring data.
Right. So I think this raises a very good point. So how can we bridge this gap between ML and networking? Like basically the idea of like networking people just doing ML themselves, or should we bring in experts from our neighboring community and do something in that space? We have seen this with programming languages and the programmable data planes, like people in the PL space joining forces with us and like building these better like verification tools and all that. So what do you take on it? Maybe I can start with Jen. Like, what's your take on this? Like, how can we start about making this happen?
Yeah, I think I think one thing that helped in getting the programming languages community connected with us was programmable devices, right? If they had to learn all the sort of 3 and 4 letter acronyms of networking and all the really frustrating constraints that fixed function networks had, it would have been very difficult to recruit, right? The learning curve would be steep and the scope for impact would be low.
Right.
And so I'm hopeful that programmability will help there. And I think what's exciting about what you guys are doing with Taurus is that the existing programmable switches are so limited. So I talked to one of my ML colleagues at Princeton. I said, oh, I want to do change point detection in the data plane. And I started talking with him about the constraints the switch imposed. And he had all these memes like you can't do multiplication and division. And I'm like, dude. And he's like, he just basically walked away. It's like, okay, never mind. I can't help you. You can't do multiplication and division. So I do think if we need the programmability helps, but we have to have at least enough primitives that they realize that they have scope to be creative and actually have a good F score or whatever when they're done. Yeah. But I think we're getting there.
Right. Yeah. Nick, do you have any?
I just want to interject. I mean, Nick brings up this good point about sort of reproducibility and sort of ML algorithms keying on things that may be not generalizable. And this is a general problem in ML. I've had instances of the ML algorithm that was designed to detect whether the face was male or female based on looking at the eyes. And at the end of the day, they figured out it was keying off mascara, right? It wasn't fundamentally, and in other instances where you've got medical imaging recognition that tells you whether you've got some lung problem because it sees a drain in the image, which indicates that there was surgery performed, right? So I think this is a problem that's recurring. I think the networking community has to kind of surface these problems to the general ML community and have them try and address them with some of the solutions that they're coming up for these other problems, but also maybe specific to networking. But I think there's certainly a problem that ML has, more generally.
I think following on that, I think you hit a raw nerve a little bit. Your question was how to bridge these two disciplines or communities, and I would say, Shabazz, you're doing it, and a few others are doing it in our community, and I think, just don't stop. Keep doing the work you're doing, and I think that's challenging. I think you've probably written some papers, and as have I, and so this is a comment to my reviewers, which is, I think if you've worked at this chasm, you're familiar with the reviewer comment that says, well, you're not inventing new ML here. You're basically just applying some model or algorithm, to a new data set or something like that, which, by the way, isn't always the case if you read a little bit more carefully. But even if that were the case, I think anybody who's basically worked in this area or like touched an ML model or tried to apply an ML model knows that basically the work isn't in the model. right? The work is not like, oh, cool, random forest done. The work is 90% of the work is getting the model to make accurate predictions on data sets that the model hasn't seen before, keying on things that are actually predictive as opposed to random spurious correlations in the data set. And that's where like the domain knowledge comes in, right? That's where like these papers that like you're writing and Binaz and Arpit Gupta and others are writing that basically require that domain knowledge, right? And a machine learning person can't actually write those papers, right? Even if you're basically doing nothing except pulling, you know, a stock model out of sklearn and like applying it to a packet trait, a machine learning person wouldn't be able to get that to work because they don't have the domain knowledge to know like, oh, it's keying off of this like packet header field, which actually has nothing to do with the important properties of the system or the environment. That's like a spurious correlation, right? Or understanding drift in the models, or understanding like what's an acceptable error rate, or understanding like the cost of retraining, or understanding the cost of extracting those features from a live packet trace. Those are things that like, you know, you with your expertise, others in this community bring to the table that I think, you know, provides a huge opportunity to bridge that gap. So I think if the gap is going to be bridged, it's probably going to be from people in this room, figuring out basically trying those models, trying to apply them, and then figuring out like, oh, actually, they don't quite work as I thought they would. And what do I have to do to actually get that to do what I want it to do? Because that's where actually all the work is.
I think that's a very good answer, like very good comment. Basically, the thing is like what's happening here, what you're mentioning is the domain expert is not an ML developer, right? Basically, when we talk to people around here, we think, oh, ML designer is the domain expert and he's going to build a model and do something. Well, that is not actually the case. This is what we are seeing here. But again, coming back to I think only I have a question here. So you have worked with image classification and these things. And again, just your thoughts on it. Who is the domain expert in that case? Like, because when we think of people like building CNNs and all these, they by definition are the image, like they are the ones who know how to do image classification and all these things. So we don't see the distinction typically in that area of image classification, because when we talk to a person who is doing image classification, he's actually the model builder, building that model and doing something. But in the case of networking, it seems like that thing does not actually apply, because there's a very big gap between an ML developer and the subject matter expert sitting in the networking. So do you have any like sort of take on like how they have bridged that gap, or how, any suggestions? Yeah.
Well, I mean, there's always collaboration.
Yeah.
Which is usually, you know, my go-to, right? Is you know, if there's an area where you feel like you could get real benefits from working with somebody else, then that's the way to try and bridge the gap. I mean, you know, Nick makes a very good point that the domain knowledge is the key, right? And so there's networking domain knowledge and there's ML domain knowledge, right? And so you want to collaborate to kind of see how to bring that you know, far, right? You know, work with you, right? I still don't know anything about networking, right? As well, but you know, our collaboration is something that has you know, provided fruit, because you brought all the ML, all the networking knowledge that was needed, and so, you know, this is an example of for how things can improve with the right sorts of collaborations.
Right.
Yeah, I'll just comment on that. I think an additional point is students and postdocs. I think we have a new generation of graduate students and early career researchers who grew up learning ML. I certainly didn't, but students often teach old dogs new tricks, right? And so it's often the case that students bring some of that are the ones who bridge the gap because they have a kind of training that their advisors don't. And so I'm excited about that. I'm always excited about that, because that to me is the key to most collaborations. Working are the students.
Right.
And when I read graduate applications now, I mean, so many of the students are interested, even if they're interested in networking, are interested in ML. Yeah. Right. And so I say that, but first of all, because they can be the bridge, but also it's a great way to attract great students, because a lot of the students are really excited about that intersection.
That's a really good point. Yeah.
I have a pithy comment to add there, which is that to your friends who are still thinking about applying to grad school, the ML bin is stacked, you know, so there are hundreds of people applying to that area who won't get in, right? But a lot of people think they want to do machine learning, but machine learning, as we were talking about right before the panel, machine learning is everywhere. Everybody's doing machine learning now. And so a lot of those people think they want to do machine learning. They might actually want to do networking. Okay. They might actually want to do machine learning applied to networking. And so check that box because I think everybody here on the stage is like interested in that, right? I mean, I view myself as basically a applied machine learning researcher. You know, machine learning as the top tier box is something that everybody's hyped about. But most people think that that's what they want to do. But in fact, what they really want to do is applications. And that's kind of what we're here for. So yeah, check the networking box.
Yeah. So Milan, do you have any comments on this?
Yeah, so I really like Kuni's comment that we need both networking domain knowledge and ML domain knowledge. And I think the subtlety always in the details. Sometimes we feel like just reading ML papers would get us the idea, but really, from my experience in working on a few anomaly detection resource allocation problem using ML, we actually have to do like low-level debugging and coding together with ML people so that we can understand how to, what kind of domain knowledge would actually help improve the model and what kind of model may better fit for the specific like characteristics of the data. So I think if we can in the future run such tutorials or workshops allows students in both places to work together on certain problems, I think that would help us improve the integration of the two fields.
So I think this is a very good. Yeah, go ahead, Milan.
Yeah, another point I think is that applying ML to networking is not only about like pattern recognition. There are a lot of like control side of problems that are also possible for applying ML, such as like traffic engineering people start working on, but network management has a bunch more management problems like placement, scheduling, resource allocation problems. So for those problems, I think today ML is kind of an addition to that. So we have formulated TE problem. So how to use ML to solve the problem? But instead, if we can work with ML people together to define new interfaces that will have ML as one building block in the system, like organically, then it will also be, provide a simulation environment so that people can plug in different types of ML solution into the problem. I think that would also be a way to improve the integration of the two fields. I think TE is especially a good case because a lot of people have been working on applying different ML techniques for TE. So maybe it's now the right time to think about how do we build a simulator or kind of automatic learning platform for TE. So that we can encourage even ML people without domain knowledge to work on this problem.
So basically, you're thinking of like more like a layered architecture here. Just like, for example, when we are writing software, we don't think of a compiler. Like as a networking person, I just write my client application, a compiler compiles it. So in your case, you are saying when we are writing these applications today with machine learning, we as network experts don't know what is wrong with the ML model, like what went wrong and why is it not giving me the right interpretation of what I was feeding into the system. So this is where you want to have the ML people to come in. So if they have better systems, if they have more automated systems to make that happen, is this the direction we should go like and look into? But how can we do it? Like how can this be done? Because how can we incentivize the ML people? Do you have any thoughts, Jen, on this? Like,
yeah, I think in general, the ML community has been really good about creating public code, libraries in Python, and there are huge numbers of data sets. And we at networking are actually pretty crummy at this, right? We have, we like find these data sets in dark corners, and we sometimes put things on GitHub, but we're not good about actually making code usable by other people. And I think there's a lesson there, right? I think if we did more to make our software systems and data sets more actually usable by others, it'd be a lot easier to attract people to work on our problems, including people that don't have a lot of the domain knowledge. So I agree with Milan completely. I think she was kind of hinting at that a bit in the traffic engineering case. Could we have some use cases that have data sets, have tools, and have benchmarks, whatever, the kind of things that would allow the ML community to actually jump in without such a high barrier to entry. It doesn't mean they don't need a domain expert to collaborate with, but hopefully at least the learning curve isn't quite so steep and they can do more reproducible and verifiable research than they would otherwise be able to do.
this might be a good time to just mention the nprint project a little bit, because I think it was so. This project was hatched by a PhD student, now graduate, Jordan Holland, who's now he's now at Netflix. But he had this kind of vision, which was like, okay, if I read papers in networking or network security, you know, and they use the word flow, right? There's 20 different representations of flow, okay? And even if I read that paper and sort of try to figure out what they did and reproduce it, even if I had the exact same data set, so like a lot of them are using like the DARPA, you know, the KDD 99 data set, or some of the stuff from the New Brunswick CIC website. Take the exact data set they're using, take the exact prose from the paper, and it's like, okay, this paper has 1,600 flows and this paper has 25,000 flows. Same data set, same, you know, same description, and yet somehow people aren't even pre-processing the data in the same way. And so one of the things that he's done in the project, and you could check it out, it's at nprint.github.io, is like try to say, okay, we're going to take these data sets like the CIC stuff or the DARPA data set. They're PCAPs. Well, PCAP has this thing called, you know, PCAP NG, right, where you can just like attach metadata to the PCAPs. And what he's done is basically label it in such a way so that, okay, here's a standard way of doing your like labeling, train test split, et cetera. Here's a library that basically will process the PCAP and split up the packets into like, here are the attack packets, here are the normal packets. Here is exactly how I did the train test split, right, for each iteration. And you just run it through the library and you get exactly what, you know, the numbers are in that paper. Now, this doesn't work like for everything, because that particular representation assumes like, I'm going to take a packet and represent it as a bitmap, right? And we just talked about like ways that models can learn spurious things. And also that doesn't have very good representations of things like time or flow level statistics. But I think it's a pretty good start, because what he's done is say like, okay, here are 8 different applications, you know, malware detection, application identification, VPN classification, et cetera. Said, here's the best known result. You know, here's the F1 score, here's the balanced accuracy, here's the paper that it was in, and here's a link to the data set with the metadata attached to it. And you can just go run it from there and like you go try to improve it. So that's the closest thing I think we have to a leaderboard.
Right.
It's not comprehensive. I mean, I think like we could run the clock out talking about ways that it's like totally imperfect, but I think we need to be thinking more along those lines.
Right. So on that point, I think this is a very interesting part. So we have seen in the computer architecture community that like looking at the data like sparse, like processing, they like if you have the data set and if you know how the data is coming in, you can come up with very efficient ways of processing, for example, in sparse computation stuff. So maybe that's another thing we need to look into, like as like, does the data that we're getting in, like giving it in the hand of the people, and they can come up with like not just the ML people, like the underlying sort of architecture people, because they can do something like on that. So Kunle, do you have any takes on it? Because you are doing work on sparsity, and like, does networking data hold such promise? Like if you see it, you can do better optimizations and build better architecture?
I mean, you can look at many examples in the architecture world of sort of, you know, people optimizing for benchmarks for data that exists, right? You saw that in the early days of you know, CPUs, or early days 30 years ago. Not so early with CPP, you know, the time where a lot of academics were focused on spec benchmarks, right, which kind of drove a whole range of innovation. And more recently, people have been looked at graph benchmarks, and now, of course, ML is driving what architects are doing. And so, if there is data, you know, in the networking space that can be, you know, is illustrative and representative of what goes on, and that is the question of sort of how representative is it. It can drive architecture, it can drive ML research, it can drive all sorts of things, because you know data is the thing that is going to reveal the sorts of characteristics that potentially could be exploited. So yeah.
Right. So Milan, do you have any comments on this? Like,
yes. So I think in addition to the data type problem, another uniqueness of network data is it comes from a variety of places. So we first need to aggregate it from many places together to do the processing. So one challenge for architecture people is like, is there any way we can build small devices or well-connected devices where they can do kind of data processing at a wide range, a large area, and do local like ML solutions that answers global questions. I think that's another challenge in addition to the data type kind of problem.
Right.
Yeah.
So I think I will bring the discussion back to this point. So we are discussing, it seems like there is a potential for ML in networking. We are making some steps both from the architecture side and then from NPRIT and like data sort of standardization part. How can, like, what other things are missing in there? How can we kickstart the pipeline? Like, again, I'm new in this space, like in research as well. Like, I'm not like that, like sort of, I recently graduated and started as a professor. So my question is, if you're telling me that, oh, we are like, the people sitting in this room are the ones starting this thing, what should be the timeline of this thing? Is it like 10 years, 20 years? Like, what things can we do based on past experiences with other things on expediting this thing? Like, so do you have any take, Jen, on like how can we go about making it like as a next step, making it happen?
Is your question like what to do next?
Yeah, what to do next, like in like making this happen, like.
Yeah, I mean, I think lowering the barrier to entry is key, and that's, data sets, that's software repositories, that's course material, tutorials like this one. I think, Nick, you have some books you've been doing that you should probably speak to as well. Because I do think the barrier to entry is still pretty high, right? If you have to be an expert in both ML and networking, that's a high bar. And obviously you don't have to be perfect in all aspects of each one to be able to get started.
Yeah.
But the more we can do to have curriculum and both in the formal sense of college courses as well as online material, I think that's certainly a big help, because a lot of this is people, right? That just need to be productive and also are making choices about what to work on, in part based on how long it's going to take to get started.
Right.
I mean, not that we should be so impatient as to only do the things that we already know how to start, but I think frankly, a lot of people do gravitate towards things they feel are in their wheelhouse because they know they have some special something special they can bring to the problem. And if the learning curve is steep and they don't know when they're done learning that they're uniquely equipped to solve that problem, they may not even start.
Right.
So I've got maybe a question to the networking researchers, because we're all academics up here. And so we all, of course, have research that is funded a lot of it by the federal government, right? So the question is, what role do the funding agencies play in engendering more ML networking research? Is there a role here?
So many questions. Let me. I don't know what the funding agency. Well, I can speak to that a little bit. Let me start with the other one that you said. How do we get started?
Yeah, how do we get started? Yeah.
I think Jen started that discussion really well with basically more exposure to material, more exposure to the building blocks, to the content. Yeah, you mentioned like that. So former student of mine, Noah Apthorpe, and I are working on a book in this area, just machine learning for networking. And I've been teaching courses in this area for a while too. And it's a funny thing because machine learning, a lot of students will take machine learning, probably yours, probably some of you as well out there. This, discussion I recently had with a student was struggling with like how to basically build a model using certain type of categorical variable, and I was like, well, why don't you just one-hot encode it and like basically throw it into a random forest or an ensemble trees? And she was like, what's one-hot encoding? I'm like, what? Didn't you take machine learning? And she's like, yeah. And I was like, well, what did you learn? She's like, well, basically linear regression and optimization, all this stuff, right? And it was like, okay, there's machine learning as it's taught as a machine learning course, which is basically somewhere in statistics or applied math or something. And then there's the stuff that like we need, right? Yeah. Bridging the gap to applications. And it's going back to what we talked about before. Like there's the theory, right? And there's the models, and then there's actually getting it to work. And I think one of the things that like I've been trying to do in my own pedagogy is like, based on like my own struggles and trying to get this stuff, is like, what do I wish that I knew? Like when I started like applying this stuff, and it's like, oh, okay, well, in the courses that I'm designing and teaching and stuff, it's like, I'm not going to basically sit there and prove theorems, but I'm going to tell you enough about how this model works. Like, so that like, is that an appropriate model for this data set, or what are the things you have to watch out for? It's like, well, when would you use like DB-scan versus hierarchical clustering? What is that? What assumptions are you making about the data? And what do you have to think about as far as parameter tuning, et cetera? Because those are the kind of things that like we need to get this stuff to work. And like students and other people who are learning, we can prove like all day long about, how linear regression, minimizes root mean square error or whatever, but that doesn't help us like when it's with the packet traces. Okay. And I think it's more of the latter. And that's, I think, like getting hands dirty, right? More hands-on, the types of stuff you're doing in this tutorial, more things where it's like, oh yeah, I understand that in theory and textbook, I understand what it does. Then there's like the actual process of getting it to work. And like, I think therein lies like the research, therein lies like the learning, therein lies like basically a whole new field, really.
Right.
I just wanted to speak to the Kunle's question about funding agencies, who I think is a great question, because a lot of times researchers are following the money to some extent. And I think a lot of the funding agencies, particularly in the US, National Science Foundation as an example, really community driven. Right. I mean, the decision about what the funding agencies choose to fund to some extent is actually driven bottom up from us, the broader us. Wish it was just the three of us, but or four of us. Sorry, Min-Lan. But the broad, but it really is the community, and I think it is about articulating a larger vision. And so I think that that's an important piece of it as well. And that's writing white papers or going to DC in the case of the US and giving talks about a larger vision so that the program managers and people higher up than that can articulate that vision further and devote funding to it. So I don't think it's sort of a passive reaction to the funding agencies. It's about creating that. And particularly, just to take one example in the programming languages area and formal verification, there's a program in the US National Science Foundation called Formal Methods in the Field, which is really about pairing someone that's a domain expert with someone who does programming languages and formal methods. And you could certainly imagine, AI in the field. I think there is even an AI in the field program at NSF as well. So you can certainly imagine creating programs explicitly to bring these pairs of, hammer and nail people together, ML people in an application domain together.
I'll say a few things about the funding as well. I think it's a good question, and I hesitate to like overgeneralize from my own experiences, because I think they're just mine. But I think I've kind of observed, I've had fairly positive experience with at least the US-based funding agencies in this regard. We like to sort of poo-poo the NSF as being like conservative and all that, but I actually think like in my own, empirical experience, I've had an easier time getting newer ideas, such as like the bridges between machine learning and networking, funded than accepted as conference papers. It is really, I've seen a lag of like 3-4 years. And it's like, man, I got all this money, I can't get a damn paper published to save my life. So I think the NSF needs to like start a conference is really what I think. No, but seriously, I think like I think what Jen said about like, the starting the workshops, like talking to the program managers, I think one of the things that's nice about the funding agencies is that, they're all different, right? And in Europe, they work differently. And I don't know totally the details of how they work, but, the NSF is probably the most merit-based in terms of like panel review, but a lot of them are ultimately driven at the discretion of program managers. And it really only takes like a visionary program manager, someone who's like, give me the next big idea, right? They're like actually not that interested in funding boring incremental stuff. Program committees love to accept boring incremental stuff, but like funding agencies, they're like looking for the next big thing. And if you talk to the program managers, like, I think you can sell them on these ideas. You can through workshops, you can build community around it. And I think, again, Shabazz, like you're doing it with this workshop. And I think SIGCOMM in the past has had these AI, NetML workshops and other things. And I think more of that will be great.
Right. Yeah. I think this is a good point. So Min-Lan, do you have anything to add to it? Like,
no, I think they're not discussion.
Okay. So I think it's interesting. So the thing that is coming out of here is for NSF to fund us, we need to sort of first make our case to them so that they can fund us.
Yeah, it's absolutely right. I mean, it definitely true of DARPA. That was the model, right? You went and convinced a particular program manager that this was a good idea, and I've been involved in starting a couple programs over the years because a single program manager was convinced that this was the future, and they wanted to, stake their time at DARPA on it.
Right.
I think it's really interesting to hear that that's also happening at NSF these days. That's encouraging. But the other thing, we were just chatting before, and we mentioned, Jen mentioned the idea of, of sort of when big data was all the rage, right? And as I remember, that was the output of a white paper from the database community, right? They got together and decided this is the future, right? And it had an enormous impact, right? And so, that's the other model, right? As you mentioned, right? Get some luminaries in the area to kind of write some a white paper saying, this is the future of the field, and that can have an impact on researchers and funding agencies and industry also.
No, that's so definitely like something that we, the new professors, have to look into. But again, I think basically like do more of these, engage a lot of people together, and sort of make your cases in front of these people. So okay, so I think we are heading towards the last 10 minutes of our panel. So what I'm going to do is, like, last question that I think that everybody will be excited about is, what do you think? Again, I know we are all struggling with it. So we talked about collecting data, we talked about building models and everything, but as a researcher, as a student coming in, folks sitting here who wants to write their next paper in that field, what should they do? Like again, networking, we see like it's getting there, it's hard, but for them, I think, do you have any other suggestions on what they can do? Like maybe move out to other communities and submit their papers there, or what plans should they do? What are your thoughts on this? Because as a student, I'm more concerned about thinking of an idea, applying it, and then getting it like sort of published out there, so that like it's accepted. Like that's how the impact will come for them. Yeah.
So I think, I mean, this conversation started with data, and I think it should end with data. We need data, and we often don't have it, but we're all using networks every day in our homes and our workplaces. And I think the more we can do to engage with the people who run the infrastructure so that we can get access to data. And that sometimes involves, deploying equipment. It sometimes involves relationship building with the people who actually are in a position to help you get data. It sometimes requires domain knowledge about new areas. We haven't talked much today about wireless and 5G, but I personally am really excited about that as an area. That's an area that also has a paucity of data sets, but I think we can all be working on our campuses to deploy, working with companies to get access to data. So I would, if I were a student starting right now, I would be trying to figure out how I can get a sort of access to data that is not readily available now, so that I can start being the one to do the first important work in unleashing research in a new kind of network or a new kind of data set for existing networks.
Yeah, sure. I would say, right. I know. Kunle keeps handing the mic to me. I don't know what that. I don't know what that means. I know. It's so mean. I guess I would say to a student trying to get started, I would just say, like, find a problem that excites you. It's something that you find exciting that you don't know the answer to. Because chances are, if you don't know the answer and it's not easily findable, like probably nobody knows the answer, and those are good places to unearth research questions. I think we're sitting in this room because we're talking about networking and machine learning, right? And I think it's tempting to basically be like, yeah, I want to do machine learning research, right? That's what it's the box. I think machine learning will find you. Okay, so if you, I mean, I've worked on a variety of problems in networking up and down the stack, right? From, performance monitoring and prediction to security to content moderation and censorship. And machine learning has like dug its claws into every single one of those problems. And so it's tempting to be like, yeah, I want to start with this hammer. Like, I want to be a machine learning person. I wouldn't worry about that these days. I think basically machine learning is going to find you. If it's something that's exciting to you, which it probably is if you're sitting in this room, I wouldn't start with the machine learning. I would start with the problem. Say, like, I'm super psyched about, like, how online social networks like moderate content, right? Or I'm really excited about, helping cellular networks, predict call drop rates, or I'm really excited about like fast online malware detection in network, or it doesn't really matter what that is, as long as it's exciting and interesting to you, because machine learning touches all of those.
Right. So Milan, do you have any thoughts on
yes,
how
I think
yeah.
suggestion how to get started is like get your hands dirty, start building tools, using the data sets as you start trying things out, even if it's just a simple problem like anomaly detection, traffic engineering. It will help you start to gain knowledge on the hands-on experiences applying machine learning, and then you're on the way to discover new problems. And also through building tools, it will be useful to a broader set of community. So yeah,
Right.
targeting the tools, start with hands-on.
Awesome. So I think we are heading to the last end of the panel. So I'll open it up for the audience, like if they have any questions. And again, it's a rare opportunity. We have an architecture, like academic and like an industrialist and entrepreneur sitting here. We have Jen sitting here. We have Nick sitting here in Milan. So we should take this opportunity and ask lots of questions if you can. So yeah, can you take it?
So my name is Kees de Laat, University of Amsterdam. So in the beginning, you started out with the benefits like more security and all kinds of magic things that machine learning will deliver when it really flourishes, So what I'm a little bit wondering about then is about the data you get, because you want to learn the machine learning, something what exceptionally rarely happens. So security violations, crypto lockers, or you name it, or failures, power failures, or flooding of a part of the country. So how do you deal with that in getting the correct balanced data to learn the machine learning, what to avoid if you have just extremely little data of what to avoid?
Oh God. Here we go again. So this is a pattern. I'm sensing a pattern here. I don't know that I have the perfect answer to your question, but from everything you've described, I mean that shows up a lot in the work that we do in the unsupervised learning area, right? I mean, if you basically have data with lots of labels and lots of labeled examples like that, that can be very suitable for a supervised learning setting. For the types of things that you describe, often unsupervised models are things that we've successfully applied in the past. And actually for those, we have had some successful collaborations with people in the machine learning community, Samori Kuptufe being one, building really fast anomaly detection mechanisms that are specifically designed for networks. But it's a very tough problem, what you said.
I mean, I don't have much to add, but if something like that is really important, in some cases, you might be able to do is build a simulator to create simulated data sets. Obviously, that means you have to trust that your simulation model is meaningful in the first place. And in some cases, maybe even controlled experiments. I mean, I think that's something you could imagine doing. I remember certainly carriers have done that in the past where they'll take a link down on purpose to see what happens. They may do it at a period of low traffic volume to minimize the impact, but I think you can do sometimes controlled experiments to help with that too. Certainly a hard problem.
You touched on issue of overfitting, but about fairness. Machine learning is not fair. It will go where there is the more data. So if there is a class of equipment that is backward and sends all data in clear text and has no concern about security and privacy, will they get a preferential treatment from the machine learning algorithm because there is more data to latch on?
I'm the non-networking guy on the panel. Someone who knows about networking.
I can comment on I can comment on the privacy, the fairness one. I think is interesting too. These are really good questions. The privacy one is really interesting because I think there's things that come up in machine learning that when you intersect them with privacy, it's like, oh, never thought of that. So Kunle, you probably work in, I don't know if you work in this area of like early exit neural nets, right? Because it's an in-network kind of thing, right? Well, it turns out that so there's certain kinds of neural nets, right, that will exit early to preserve computation, very useful in sensor networks and other things, power saving, et cetera. Problem is, if those early exits happen like in ways that are imbalanced across classes, someone who's basically watching the behavior of that network has now basically observed the side channel because it's like, oh, it's exiting early. That means it's more likely that it's class A than class B, et cetera. And so these are cases where, again, I think obstacles, but opportunities for researchers to work in. Because this is one actually, Hank Hoffman and his student Tejas, we collaborated with some architecture folks in this area because they're like, oh, there's this early exit neural net stuff. Like, do you see privacy risks here? And it's like, oh yeah, there are. And then I don't know very much about like designing these neural nets, but in working with the architecture folks, I could basically talk about, okay, what are the adversarial models we have to think about? What are the privacy leaks we have to think about? What are the right models for data leakage? And I think there is a collaboration between like networking and architecture folks that work that pretty well. As far as fairness, like, I don't know what to say there too much. I'm gonna leave that one actually. I think one thing I will say is that like we haven't done too much work in fairness and network modeling, but one area we have worked in is encrypted DNS performance, and you observe significant disparities in performance in North America versus developing regions, certainly sub-Saharan Africa, but also certain parts of Asia, where these architectures and protocols are basically optimized for the Western world. And so when we talk about models that are like, hey, I'm going to predict page load time or whatever based on network metrics, et cetera, use a data set that's like basically only gathering data from a certain part of the world or whatever, I wouldn't be surprised if those models were basically tuned and optimized for people in those regions. And I don't think our community has really dug into that much yet because we're still trying to basically make the models work. But that's probably the frontier, I think.
Yeah. So I was not here earlier today, so I might be repeating some of the things talked. But circling back to this workshop about data plane and machine learning in the switch data plane, I'm wondering if we could have some discussion on what do we see as the killer applications? Is it going to be more on the training side? Is it going to be more on the inference side? Is it going to be more for network applications like classification or security? Or do you see switches helping more generic ML applications? When might the data plane suffice? When would the control plane help? Do you see impact more on the data center side or in the ISP side? So
I mean, the initial work that we've done on Taurus is putting the support for ML in the data plane such that you can look at every packet and do inference on it and make decisions based on predictions that the ML model provides. The most obvious place to use it is in security, anomaly detection, and look at packets that could potentially be malicious and deal with them appropriately. But you can see other work, and Nick and Jen can tell you much more about the potential in other areas of resource allocation and load balancing that you could do in the network. And of course, in terms of building the model, you'd like to have as much information about what's going on in the network as possible and be as centrally located as possible. That's not always possible. And so you can think about building models that are more federated, more distributed, that achieve in concert, what you might do more centrally. So yeah, I mean, and in terms of inference versus training, you could probably get away today with doing the training in the control plane, passing the information up from the data plane, but inference, you get dramatically better results, more accuracy, dramatically by orders of magnitude better if you can do the inference in the data plane.
Yeah, I completely agree with everything that Kunle just said. I'll just add that I think performance problems are also a good avenue because they often, I mean, if you take something like NetFlow or IPFix data, you're doing like 1 in 5,000 or 1 in 10,000 packet sampling. You can use that to find big flows, but you're not going to be able to look at a pair of, consecutive packets of the same flow and understand the throughput problems or packet loss or packet reordering or video quality of experience. I know Nick has done some work in that space. Those kind of things really need to look at the relationship among packets in the same flow. And that kind of thing really requires packet level analytics. Now, whether it needs ML or not, that might vary from one problem to another, but the need for packet level analytics, I think, arises certainly in security, but also in performance analytics.
Actually, Jen, I think you hit on a really good point here, which is sort of and going back to some of the earlier comments that we talked about where, everybody wants to talk about models, right? But it's really about data representation. And your comments reminded me of like, my early collaborations with Samori Kuptufe on these problems, like designing anomaly detection, unsupervised learning models for network data. It was like, oh yeah, I got all these data sets. Basically, in summary, there were sort of NetFlow style summaries of smart home traffic. And he was like, this data is garbage. He's like, it's basically NetFlow. He's like, I want packet traces, right? Because you basically have already assumed, with your representation here, what's important, right? And Jordan Holland's thesis on nprint was the same. It was like everybody's starting with NetFlow, assuming that this aggregate representation, you've already basically assumed the representation. Like, give me the raw data, and that's 100% right. And it's also very challenging from a systems perspective, as you point out, because packets are big, nprints are huge. You can't basically gather all this. You're certainly not going to basically do it all on the switch. You're not going to store it all. You're not going to ship it all off. So you have to make some really hard decisions. And I think that I think we really haven't even scratched the surface on that intersection yet. Is like, okay, the magic is in the representation, like how we basically represent this data to these models, and how do you basically trade off the systems costs of like creating those representations with what we really need to present to the model so that they can make the right inferences.
Well, do you have anything? So maybe we'll take the next question.
Okay, so I've heard quite a lot about data, that's how important that is. But I think that I missed the part that how we can get the data, or how we can convince those who have data to give us the data, or the other way of saying that, why should they give up the power of having the data to us?
I mean, I think a piece of what I was getting at earlier in the discussion is I think we can work with as academics, working with our local campus IT organization. It's not always easy. Those are human relationships take time to build, but all of us are on networks all the time. We're on one here right now. We're on one on our campus. And so I think that's an opportunity to work. I mean, work locally, in terms of getting access to data. And in doing that, I mean, part of building the relationship is convincing the people you're working with that the data you're collecting is going to bring value to them, that you're going to be able to tell them things about their network they don't already know, and maybe circle back to them and make their networks better. And so it's a bit of a two-way street to get them motivated. But certainly when I worked at AT&T, that was how we formed relationships with network administrators and gave them value. And working with the campus IT staff, it's at a smaller scale, obviously, but I think similarly, we're trying to bring value to them so that they want to play with us, including in some cases, applying for funding to support the person in their group that's helping us, which I've done before. And it's a lot of work, but you have to create the people that are going to help grease the skids.
Yeah, I learned a lot as a PhD student, actually working with Jen on at AT&T on problems exactly like this. And so I think she hit the nail on the head again. But I think to put an even finer point on it, I'll quote one of our former colleagues, Randy Bush, who, when I was working on my PhD thesis, he said something to me which kind of it kind of shaped my whole approach to research throughout my career, which is he said, you know, everybody wants data. A lot fewer people know what they're going to do with the data once they get it. Okay, so instead of seeking out the data, try to basically seek out problems that people want solved. And if you work on those problems that people want solved, the data will find you. And that was true in my thesis. I wrote a tool to basically debug router configurations. And then I went from basically having to ask people for router configurations so that I could write the tool to people just like sending me like their configs to like help them debug them. And so it was the story that Jen just mentioned, which is like, work with the people who need the problem solved, and like the data problem basically just goes away. You'll have more data than you know what to do with. I've found. For me, as a researcher in this area, like zeroing in on the problems, I have more data than I can handle. Actually, the problems are really more like, are we working on the right problem? And also, like, is the problem that I'm working on, is the solution is it going to generalize? Right? Okay, I've got this really cool data set from like Verizon or AT&T or Google or Microsoft or whatever. And I built this model that basically does, you know, X, Y, or Z, performance prediction or anomaly detection or model drift detection. But how do I know it's actually going to work outside of that particular context is something that I spend more time worrying about, frankly.
Yeah, I think basically, like, I think it's the end of the panel. So I think we had a very interesting discussion. Thank you for amazing questions. Again, the thing is, we have a Slack channel. We have if you have any other further questions, please ask us and we can route them to them and get you some sort of reply to those questions. But overall, let's thank our panelists. Thank you so much for being here and flying all the way from, again, to Tunle, to fly all the way from the US here to give a talk in the networking community. So again, thank you, everyone. Thank you so much. So Milnet,